Have you ever wondered how scientists can measure gravity with high precision using surprisingly simple equipment? In this video, we'll explore a clever device called a reversible pendulum and show how it allows us to determine the effective gravitational acceleration on a celestial body, such as the Earth, through careful measurements of oscillations. Let's see how physics and precise timing come together to measure one of the most fundamental quantities in nature. The reversible pendulum I will use is a metal rod with a movable weight and two axes of rotation. By sliding the weight along one end of the pendulum, its center of mass also moves, but it always remains between the two axes of rotation. The sum of the distance a1 of the first axis of rotation from the pendulum's center of mass and the distance a2 of the second axis of rotation from the center of mass is therefore constant and equal to the distance Lr between the two axes. A reversible pendulum is a special type of physical pendulum, so the relation for its period of oscillation t, which I introduced in the previous video titled Measure Gravity Almost Anywhere with a Physical Pendulum, also applies here. In that video, we showed that the dependence of the period t of a physical pendulum on the distance a of its axis of rotation from its center of mass is quadratic, and we also found the minimum of this dependence. In the equation, Gf represents the effective gravitational acceleration, which includes the influence of the rotation of the celestial body on which the pendulum is located. For example, on the rotating Earth, we experience this effective gravitational acceleration, which is approximately 9.81 meters per second squared. If we express the two roots a1 and a2 from this relation, for which the period of oscillation is Tc, we would find that their sum, Lr, is equal to the ratio Tc squared multiplied by the effective gravitational acceleration and divided by 4 pi squared. Therefore, if we determine the common period Tc for two distances a1 and a2 and measure the sum of these two distances Lr, which in the case of a reversible pendulum is simply the distance between its two axes of rotation, we can calculate the effective gravitational acceleration at the location of the pendulum. The distance Lr can be measured with a ruler. However, the common period Tc appears squared in the equation, so it must be measured as precisely as possible if we want an accurate value of the effective gravitational acceleration. One method is to change the distances a1 and a2 of the reversible pendulum gradually by sliding its weight, and then measuring the period of oscillation for each of these distances until we finally find a common period Tc, which is, within our measurement accuracy, the same for both distances a1 and a2. The change of distances a1 and a2 will be represented by the distance d of the pendulum weight from the end of the rod. For distance a1, the weight will be above the current axis of rotation, and for distance a2, the weight will be below the current axis of rotation, because we flip the pendulum and hang it on its second axis of rotation. Thus, with one position of the weight d, we can measure two corresponding periods of oscillation, t up and t down, simply by rotating the pendulum by 180 degrees and suspending it from the other axis. Using an optical sensor and software that can communicate with it, such as the IP Coach program, we can measure periods very quickly and with good precision. If you don't have an optical sensor and software that can communicate with it, you can record the oscillations on video and measure the periods from the video. Again, we must keep in mind that we need to measure small oscillations with a maximum angular displacement of about 5 degrees, so that the approximation holds that the sine of the displaced angle is approximately equal to the angle itself in radians. This approximation was used when deriving the equation for the period of a physical pendulum that we started from. Without an optical sensor and software that communicates with it, measure 10 oscillation periods for each position of the weight, that is, for each value of d, with the weight down, and 10 oscillation periods with the weight up. The coach program, for example, communicates with the optical sensor. It quickly records 10 passes of the pendulum rod through the optical beam, 10 time measurements corresponding to 5 periods or 10 swings. From the straight line fitted through these 10 time points, the program calculates the average swing time, which is half of the oscillation period. In this way, we can quickly measure the dependence of the oscillation period, or swing time, for the weight located up on the distance d, and the dependence of the oscillation period, or swing time, for the weight located down on the same distance d. The swing times are half of the oscillation periods, t up and t down. Let us change the distance d, for example, 9 times. This means measuring 18 data points, 9 points for each of the two graphical dependencies. Here I am showing in the coach program the measurement of 2 additional swing times for another position of the weight, determined by the value d equals 81.5 millimeters. First, I again measure the swing time of the weight below the center of mass, labeled here as TD, and then the swing time for the weight above the center of mass of the pendulum, labeled in this program as TU. We then fit straight lines to both measured dependencies using the least squares interpolation method, and the intersection point of these two lines determines, with sufficient accuracy, the common swing time TSC, which is equal to half of the common oscillation period TC. In this video, we demonstrated how a reversible pendulum can be used to measure the effective gravitational acceleration by finding two different pendulum configurations that share the same oscillation period. By measuring the distance between the two axes of rotation and precisely determining this common period, we can calculate the local value of gravity with impressive accuracy using relatively simple equipment. If you found this video helpful, don't forget to like it and subscribe to our channel. Your support helps me create more high-quality content. Thanks for watching, and I'll see you in the next video.